Greetings everyone. Today we will be developing a unique ID generation service. But before we delve into the requirements, let's analyze the system using a 4-question framework. The first one, what does this service do? So this service is designed to generate unique IDs, which can comprise of numbers, alphanumeric characters, or even the GUIDs. The second is, why do we need this? In a highly distributed system, millions of events occur every second, such as tweets or comments on a Facebook posts. It is imperative to assign unique IDs to these events to ensure that they can be identified easily in the future. Okay, now who are our customers? Our customers could be internal services within our organizations, or we could extend this service as a public cloud service to onboard enterprises or independent software developers. However, for this session, our customers are internal services of our organization. Finally, the last question and the most important one, how the customers will interact with our system. This analysis helps us to comprehend the system and design appropriate interfaces. Thus, we should create APIs to enable our customers to access unique IDs whenever required. Great. Now we have understood the system. Let's move on to the defining the functional requirements. And our functional requirement is to generate monotonically increasing globally unique identifiers. So if we look carefully, we have two sub-requirements of the system. The first one is that we have monotonically increasing, and the second one is a globally unique. So what exactly does a globally unique identifier mean? It's in simple terms, it refers to a number that is one of a kind. And by unique, I mean that every time you request, it will never generate the same number again. This holds true whether you are using the same computer or different computer or hundreds of computer or even the entire duration of your system's lifespan. So if we assign this ID to our events, there won't be any collision in the lifespan of the system. Monotonically increasing, it means that something is constantly increasing or growing in the value without any decrease or fluctuation. In other words, the value of the variable or quantity is in question is always moving in a positive direction with no reversal or dips. Right. So to clarify, our goal is to create globally unique IDs that are incrementally increasing, such as, so for example, we can have 1, then 2, then 4, 6, 8, 10, 100, etc. However, it is worth noting that these IDs do not necessarily have to be in a conjugated numerical order. So for example, I don't need these numbers to be 1, 2, 3, 4, 5, 6, 7, 8. No, it works, it is okay, but not really needed. So with our functional requirements now firmly established, let's proceed to defining the non-functional requirements. So our aim is to ensure that our service is highly available. This is crucial because there are numerous services, possibly in hundreds or thousands, that depend on our service. Any disruption or downtime to our service would severely affect the availability of these other services. Furthermore, we desire our system to be scalable as new services are created within our organization and subsequently they onboard to our service. Our system should have the ability to scale up and expand accordingly to meet the demands generated by these new services. Let's now turn our attention to the scale at which our system will operate. Since our service will be responsible for generating unique IDs, right? So we need to consider how many requests the system will receive each day. So our system should be capable of generating 10 billion unique IDs per day. So to put this perspective, let's do some calculation. So we have approximately 10 billion, right? Billion can be turned into as 10 to the power 3 into million per day, right? And with the formula we know that we can have million per day can be rewritten as 12. This 10 can go and come as 120, and then this 10 power 3 can come as 120k. So this request becomes 120,000 RPS. So this equates to an average load of 120,000 requests per second. It is worth noting that this is an average load and the actual load will fluctuate throughout the day with some peaks and some periods of no request at all. So nevertheless, being able to handle a load of 120,000 RPS is a good starting point. As we discussed earlier, our system should be able to generate globally unique IDs for the entire lifespan of the system. So the next question should be, what is the lifespan of the system? And the answer is 10 years. So let's do calculate how many IDs we will generate over this period. So we are going to generate 10 billion IDs multiplied by 1 year, which is 365, multiplied by 10. We can convert this 365 to 400, and that turns out to be 40, 10, 400, and this 10, 4,000. So 4,000 billion, which comes out to be 40 trillion IDs. Okay, so now we are going to generate approximately 40 trillion IDs per second. So now let's move on to discuss the interface, right? So with regards to the interface that our customers will use to interact with our system, we'll expose an API that will generate a unique ID each time it is called. It's also worth considering whether we should implement the capability to generate IDs in batches, such as returning like 100 unique IDs per API call to avoid repeated API calls. And this is a question that we should be discussing with the interviewer and then proceed accordingly. For this session, however, we will only implement the generate ID function, which will return only one ID for every call. Let's focus on designing the high level structure of our system. At the top level, we will be having a client service, which are actually our customers. And then we will be having a backend ID generation service. The customers are going to call the generate ID function and then receives a response. The design looks very straightforward and uncomplicated. The critical aspect of our system is how we will generate monotonically increasing globally unique IDs. We should concentrate on this aspect and explore various approaches, evaluate their advantages and disadvantages, and ultimately decide on the best solution of our problem. The first super simple approach could be using the GUIDs. Is it feasible to employ a GUID? It is a popular technique utilized in few databases like Cosmos DB. GUIDs are 128 bits long and it allows them to easily accommodate 40 trillion unique IDs. Generating a unique GUID, which itself it's a straightforward process in all programming languages with methods like GUID.createGUID in C# or similar functions in Java or Python. One notable aspect of GUIDs is their extremely low likelihood of producing duplicates. Some documentation even states that generating thousands of GUIDs per second for the next 1000 years is unlikely to result in collisions. However, in our case, generating 120,000 GUIDs per second, and in peak load it could be 500,000 GUIDs per second, which increases the likelihood of duplicates. As a result, using GUIDs could be a deal breaker. If we take a look like we are going to store 40 trillion unique IDs, and if you recall, unsigned long data type, which is a 64-bit number, and it is also capable of storing 40 trillion unique numbers. Why would we adopt for 128-bit storage, which would increase not only the storage size but also our index size in database? Additionally, since GUIDs are completely random, they have no ordering in that. So they do not fulfill our requirement for monotonically increasing IDs. So combining these all four five situations, we will not move further with the GUIDs. Let's move on and investigate other potential approaches. Is it possible to implement a counter-based approach using a base counter variable that increments each time a request is made? This would ensure that the generated numbers are unique and always increasing. However, if multiple requests are made concurrently, we need to consider how to handle this. One solution could be like to use a synchronization construct to ensure that one thread increments the counter at a time, although this may impact the response time, but it may be a good start. It is also important to note that counter variable is actually stored in the memory, which means that if the machine reboots, the counter will reset to 0, and when the machine will come back, it will start again generating the values from 0, 1, 2, 3, means that duplicate IDs may get generated. To avoid this, we may need to store the counter in a persistent storage like a database. However, writing to disk can significantly slow down the system, especially when you are handling up like 120,000 requests per second or even half a million at peak times. So we need to find a way to address this issue. You might want to pause the video and reflect on possible solutions. One possible solution to avoid generating duplicate IDs after a server reboot is to implement a strategy where we write the counter to the database after a certain number of requests or a defined interval, such as every 1000 requests. For example, when the counter reaches to the multiple of 1000, we save it to the database. And if the server reboots, we start from the last saved counter value plus 1. So to illustrate this, suppose that the request arrives at the ID generation service at time t1 and the counter value is 1000. We save this value to the database and return the ID of 1000 to the client. Right. Later, another request arrives and at that time the counter value was 1499. Now the ID generation service will increment the counter and it will return 1500 to the database. Now suppose at this moment the server reboots. After a certain time, let's say server comes back and the client service asks for a new ID. So what the ID generation service is doing is going to read from the database and it gets the last ID as 1000 and then increments the value 1 and returns the counter to the client service, which is incorrect. We can see that this approach is still leading to generate duplicate IDs if the server reboots before the next interval is reached. So we might want to fix it, right? How can? Please pause and reflect on the possible solutions you can find for this particular problem. An effective solution to avoid generating duplicate IDs is to set the base counter value to last ID plus X when reading the last ID from the database, and X is your incremental value. So for example, like suppose that request coming to the client service and then ID generation service read the last ID from 1000. So now we got the last ID is equal to 1000. I will add 1000 in that because my incremental interval at which I am saving is 1000. So now my base counter value is 2000 and I will write down that value to the database. So now last ID is 2000, and then I will keep on incrementing the counters of starting from 2000 to generate the IDs. Right now, suppose that at this moment my ID generation service crashes after generating 2001, and it comes back, it reads the value from 2000, and then it will start from 3000. It basically avoids the interval at which, because it is not aware at which state you had been crashed or rebooted. So this helps you to avoid generating duplicates. So now we have resolved the concurrency issue by implementing a synchronization construct and address the server reboot problem using persistence. While the system works well on a single server, we need to consider scalability when running it on multiple web servers. If multiple requests with the same counter value reach two different web servers at the same time, both will generate the same ID, and this will result in duplicates. To avoid this issue, we can incorporate the concept of machine ID, which is a unique ID assigned to the server in the fleet. And then by combining the machine ID with the generated counter, different machines will produce distinct ID. This approach shows the potential in preventing duplicate ID generation. Let's explore a few examples to further illustrate this concept. Instead of using unsigned long 64-bit number as an example, I am going to use a simple 4-bit number just for easy calculation. So now let's say we have 4 bits, and most significant side is representing your machine ID, and the least significant side is actually representing the counter. So now let's say on our fleet we have two servers, server A and server B. So server A has machine ID of 00, and server B has a machine ID of 00. 01. Now suppose that the first request came to this, and both the servers have the counter set to 0. Now suppose the first request came to on server A, which generated a value of 00, and that means effectively is 0, and on this it is 0100, which is effectively 4. Now suppose the next request comes on to server A, and it generated a counter of 1, which is 0001, and that means 1. Now you can take a look, right? So first it generated 0, then it gone to 4, and then it gone to 1, which is actually got decreased. So now the IDs are depending on which request it is landing first, so there is no guarantee of having monotonically increasing ID in this particular combination. So what else we can do right now? So one approach that we can do is again switching the counter and the machine IDs. So now your counter is on the left side, or you can say it's a most significant side, and the machine ID on the least significant side. Let's see if it fixes this problem. So same server A, server B, its ID is 00. Sorry, it's a 0. Let's make it 01 here, and this is the counter, and this is 00, and this is your counter will be. So request came to 00 here, it generated 0. The counter is 00, it generated value of 1. Now this got a request of second request, so it is 0100, its value is 4, and on this it got 0101, which is actually generating 5, and then request came on this side, so it generated from 2 to 3, so it is 102 and 00, so it actually became 8, and this was counter, right? So it becomes 2 now, it's 1001, and it generated 9. Now suppose the next request came on this server itself, so it became 1 1101, which is actually how much? 8 4 12 1 13. And in this was the counter position, so it becomes 1100, and it is actually became 12. So now you can see, initially we thought it is actually monotonically increasing, but it actually got to, so we can see that initially it looks like it was generating the monotonically increasing number, but we saw that it is not guaranteeing that value. So we saw that value gets decremented after that. And so the IDs are dependent on the sequential order on which server the requests are reaching, right? So this is not good for monotonically increasing ID requirement. If let's try to find another solution that fixes this problem. Let's evaluate a centralized solutions that may generate a monotonically increasing IDs with certainty. So for instance, we could use a SQL database with auto-incrementing primary keys. And whenever a request comes in, we had a record in the database and return the primary key, which is going to be our unique ID, and which is guaranteed to be both unique and monotonically increasing. However, what happens if the SQL database goes down and service availability is compromised? We could add a replica of the database so that if the primary fails, we can rely on the secondary, but this leads to a question of our replication strategy. If we use asynchronous replication, some records may not be replicated when the primary caches, resulting in duplicate IDs when the secondary becomes the primary. So for example, we had a ID 4 which was added to the primary and it crashes, but the 4 has not been copied to the secondary, and when the secondary takes over, it starts generating the ID of 4. That means that now we have duplicate ID. So asynchronous replication have this drawback, and if we use synchronous replication, this would guarantee to have a unique ID, but this would negatively impact the performance because now I have to write down two different databases and the latency between these two. Moreover, when we are writing, a single database instance may not be able to handle 500,000 requests per second. So this centralized approach meets our functionality requirement, but it does not meet our scalability requirement. An alternative approach to generating monotonically increasing ID is to use time as it always increases in a sequential manner. However, this approach only works on a single server and has similar limitations when running on multiple servers. We might have to tweak things out to get it working on multiple servers. One challenge with using time as a basis for ID generation is that it relies on the clock of the system, and if multiple servers are involved, the clocks on these systems must be synchronized, and if any clock drifts off, it needs to be resynchronized, which could result in the time moving forward or backwards and the possibility of generating duplicate IDs. Considering these challenges, it may be necessary to discuss the guarantees of monotonically increasing IDs in these rare scenarios. Depending on the outcome of the discussion, we can choose the path forward. For the purpose of this discussion, let's assume that it is acceptable to generate duplicate IDs caused by clock synchronization issues. Let's understand Twitter's snowflake, which is actually based on the epoch time. It is a 64-bit long data type and different bits represents different thing. So the first bit is sign bit, which is actually to ensure that any programming environment using these identifiers interpret them as positive integers. A sign bit is assigned to these identifiers and its value is always set to 0. This means that the overall number is positive with a single bit acting as a marker. So next is the timestamp, which is actually 41 bits, and these 41 bits are assigned for millisecond. The Twitter Snowflake default epoch will be used, and its value is November 4, 2010. We can also initiate our own epoch when we deploy our system. So for example, March 25, 2023, 12 midnight. So if we do some calculation, right, uh, the maximum time to deplete this range is like 2 to the power 41 divided by 365 number of second, number of millisecond. That comes out to be close to 70 years. So if we are starting from today, we are good for 70 years to use this system. The next is data center ID and the machine ID. So combine these two bits, which is actually 10 bits, they can uniquely identify a particular machine. So that means that we can have up to the power 10, which is 1024 machine can uniquely be identified and can be the part of this ID that can help you to uniquely identify the machine. The next is a sequence number. It is actually a local counter for each machine, and it keeps on incrementing one, just like a counter based approach that we did earlier. The number reset to 0 to in every millisecond. Theoretically, a machine can support up to a maximum of like 4096 new IDs per second. So some of the benefits for the Twitter Snowflake approach is like it's a sortable by time. So because we are using a timestamp, and that is actually on the most significant side of the number, we can actually sort them by time. They are scalable as it can accommodate like 1024 machines. The cons for this is that it requires third-party service like zookeepers to maintain the machine IDs, right? Uh, since it is reliance on time, and we discussed it earlier that it is possible to move the time backward, in that case it is able to generate a duplicate ID. The interesting part is that when there are no requests coming to the system, the IDs that can be generated during that system could be lost. The other thing that is some sort of like cons is that the ID generated by these by this snowflake based approach is like they are predictable. Now let's talk about how to generate the IDs in the Twitter Snowflake. So first we can start with a long ID. We can declare the variable long ID, which is equal to 0, right? And then we can generate an epoch timestamp and assign it to ID, which is timestamp right now. Then now we have to append the machine IDs, which is actually your node ID. So for that, what we are going to do is that we take the existing ID, we do left shift by the number of bits, which is actually 10. So here we will shift the ID by 10 bits on the left side, and then we OR with the actual node ID of that particular node. Now once we have done that, now it's for time for adding the counter. So for that we do the similar thing. We will shift the ID again by counter bits, and then we do the OR with the counter ID. Just wanted to add information here that like Discord uses a snowflake, and Instagram also uses the snowflake, but it's a bit modified version of the data format. They use different number of bits for node ID and the counter. So with this, let's review our design. We have discussed the process of generating the unique ID, starting from the use of the GUIDs, counters on a single machine, and then multiple web machines. We talked about the centralized approach, and finally a time-based approach using Snowflake. While the Snowflake approach can generate monotonically increasing unique IDs, still there is a possibility of duplication if the time clock moves backward. And in terms of non-functional requirements, our system is highly available, as each machine can generate up to 4096 unique IDs per millisecond, and it can accommodate up to 1024 machines for scalability purpose. It is essential to discuss the pros and cons of different approaches because in the end it is all about trade-off. And with that, let's conclude this session and looking forward to seeing you in the next one. Thank you. Bye.